Right now, tonight, if you step outside and look up, you see stars, maybe a few dozen, maybe a few hundred, if the sky is really dark and clear. And your brain does something automatic. It looks at those stars and it says, okay, I've got a pretty good picture of what's out there. A handful of bright dots scattered across the darkness. That's the universe. That's the whole show. And here's the thing. That picture is almost entirely wrong. What you're seeing when you look up at the night sky is a tiny, misleading, almost laughably incomplete sample of what actually exists. It's like looking through a keyhole and thinking you understand the room on the other side. You're not seeing the universe. You're seeing a sliver of it, a fraction so small it doesn't even register as a fraction. The stars you can see with your naked eye on the clearest night of your life, all of them combined, amount to maybe a few thousand stars. A few thousand out of hundreds of billions in our own galaxy alone. And our galaxy is just one of trillions. So when you look up and feel like you're taking in something vast, you're actually looking at the cosmic equivalent of one grain of sand on a beach that stretches further than you can imagine. And that beach? It goes on and on and on. Tonight, we're going to pull back that curtain. We're going to strip away every comfortable assumption you've ever had about the size of things. Because everything you think you know about scale, about distance, about how big the universe really is about to be shattered. And trust me, by the end of this, the night sky will never look the same to you again. It shouldn't, because you'll finally see it for what it actually is. Before we can even start talking about galaxies and superclusters and the observable universe, we have to deal with a problem first. And that problem is your brain. Not because there's anything wrong with it. Your brain is incredible. It's the most complex object we've ever found in the known universe. But it was built for one specific job. It was built to help you survive on a small planet, in a small neighborhood, dealing with distances you could walk, drive, or maybe fly across in a few hours. Your brain was never designed to understand a light year. It was never built to wrap around the concept of 1 billion kilometers. And when you try to force it to, something breaks. Not dramatically. You don't feel confused exactly. You just feel nothing. The numbers stop meaning anything. They become words. Just words with a lot of zeros. And that's the trap. That's where most people get stuck when they try to understand cosmic scale. The numbers get so big that they actually stop being impressive. They just become abstract. So here's what we're going to do. We're going to cheat. We're going to take these impossible distances and shrink them down into things your brain can actually feel, things you've touched, walked past, held in your hand. If the solar system were the size of a football field, where would you be standing? If the distance to the nearest star were a road trip, how long would it take? If the observable universe were a grain of sand, how big would a single galaxy be? These comparisons aren't perfect. Nothing is when you're dealing with scales this enormous, but they're the closest we can get to making the impossible feel real. And once your brain starts to feel it, once it stops just hearing the numbers and actually starts to grasp them, everything that comes next will hit differently. So let's start small. Let's start somewhere you can actually picture. And then let's build from there, one step at a time, until the scale becomes genuinely, uncomfortably, beautifully overwhelming. Okay, let's start with something you've looked at your whole life, the moon. It hangs up there every night, bright and familiar, close enough that it feels almost reachable. Like if you just had a really, really long ladder, you could climb up and touch it. And here's the first thing that should mess with your head a little. The moon is not close. It feels close. It looks close. But the distance between you and the moon right now, as you sit here, is about 384,000 kilometers. Let that number sit for a second. 384,000 kilometers. Now, if you tried to drive there, bumper to bumper, no stops, no sleep, just pure highway at highway speed, It would take you roughly 5 months. 5 months of non-stop driving just to reach the thing that looks like it's hanging right outside your window. If you tried to walk it at a normal walking pace, day and night, no rest, it would take you about 8 years. 8 years of walking to reach the moon. If you tried to fly there in a commercial airplane, like a 747 flying at cruising speed non-stop, it would take you about 19 days. 19 days of flying straight up to reach something you can see with your eyes. And here's the thing that really puts it in perspective. It took humanity decades of research, billions of dollars, and some of the most brilliant minds in history just to cross that distance. And we only did it a handful of times. The Apollo missions, the ones that actually put human beings on the lunar surface, took about 3 days to get there. 3 days traveling at speeds no human had ever traveled before. Thousands of kilometers per hour. And even at that speed, it still took 3 days. The moon is our nearest neighbor, the closest thing in space to Earth. And it took everything we had just to get there. If that's our nearest neighbor, think about what's next. Because the next stop on our journey isn't even in the same ballpark, not even close. The moon was just the warm-up. And trust me, the warm-up is about to end. All right, the moon felt manageable, right? A little uncomfortable maybe, but manageable. Now let's make you uncomfortable. The distance from the Earth to the Sun is about 150 million kilometers. 150 million. Let me put that in context using what we just talked about. Remember how the moon was 384,000 kilometers away? The sun is about 390 times further than that. If you lined up 390 moon trips end to end, that's one trip to the sun. That drive we talked about to the moon, the 5-month drive, multiply that by 390. That's over 160 years of non-stop driving to reach the sun. You wouldn't make it. Not even close. Your great-great-grandchildren wouldn't make it. And yet, every single day, light from the sun is making that trip in about 8 minutes. 8 minutes and 20 seconds, to be exact. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, takes over 8 minutes to bridge the gap between us and our own star. Think about what that means. When you look at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. That light left the sun 8 minutes before it hit your eyes. Now here's why this distance matters so much. Astronomers needed a measuring stick, something they could use as a standard unit to map out the solar system. So they invented one. They called it the astronomical unit, 1 AU. And 1 AU is simply the average distance from the Earth to the Sun, 150 million kilometers. 1 AU becomes the ruler that astronomers use for everything inside our solar system. Mercury is about 0.4 AUA from the Sun. Venus is about 0.7. We're at 1. Mars is about 1.5. And as we start moving outward to the outer planets, those numbers get big fast, really fast. And that's exactly where we're headed next, because the solar system is about to get a lot bigger than you thought it was. Okay, I need you to forget every solar system diagram you've ever seen, every poster in every classroom, every animation in every documentary. Every single one of them is lying to you. Not on purpose, not maliciously, but they are fundamentally, wildly, outrageously wrong about one thing: the distances. Every solar system diagram you've ever seen has the planets packed together like marbles in a jar. Sun in the middle, planets lined up around it, all nice and neat, all close together, all visible in the same frame. That's not what the solar system looks like, not even a little bit. The real solar system is almost entirely empty space. Brutally, shockingly empty. If you actually drew the solar system to scale, if you put the sun and all the planets at their real distances from each other, Most of the planets wouldn't even be on your screen. They wouldn't be on your wall. They wouldn't be in your room. If you made the sun the size of a basketball and placed it in the middle of a field, Earth would be a tiny speck, smaller than a grain of sand, sitting about 26 meters away. And that's one of the closer planets. By the time you get to Neptune, the outermost major planet, it would be sitting about 780 meters away from that basketball. Nearly a kilometer from a basketball, and there would be almost nothing in between. Just empty space. Vast, cold, dark, empty space. That's the solar system. Not a cozy little neighborhood with planets all hanging out near each other. It's an ocean of emptiness, with a few tiny specks of rock and gas scattered across it. The distances between the planets are so enormous that if you shrank the entire solar system down to fit on a football field, most of the planets would be invisible. You wouldn't be able to see them. They'd be too small and too far apart. The solar system looks crowded in textbooks because textbooks can't show you the truth. The truth is too big, too empty, too uncomfortable to fit on a page. And if the solar system, our own backyard, is this empty, this vast, this incomprehensibly spacious, just wait, because we haven't even left the neighborhood yet. Let's take a trip. We're going to hop from planet to planet, starting from Mars and working our way out to the edge of the solar system. And at every single stop, I want you to feel how much bigger the last jump was compared to the one before it. Because that's the thing about the outer solar system. Every step outward doesn't just get bigger, it gets absurd. Mars first. Mars sits about 1.58 U from the Sun, which means it's about 1.5 times the Earth-Sun distance away from us at its closest approach, and much further when it's on the other side of its orbit. Even at its closest, a signal traveling at the speed of light takes about 3 to 22 minutes to reach Mars, depending on where the two planets are in their orbits. Now jump to Jupiter. Jupiter sits at about 5.2 AU from the Sun. That's 5 times further from the Sun than we are. A light signal takes anywhere from 35 minutes to over an hour to reach Jupiter. Over an hour for light to get there. Light, which crosses the entire Earth in a fraction of a second, takes an hour to reach Jupiter. Now Saturn. Saturn is at about 9.58 IU, nearly 10 times the Earth-Sun distance. Light takes between 1.5 and 2 hours to reach Saturn. 2 hours. And the images you see of Saturn, those stunning rings, that golden glow, that light left Saturn 2 hours before it ever touched your eyes. Now, Uranus. Uranus sits at about 19 AUTU, 19 times further from the Sun than Earth. Light takes between 2.5 and 3.5 hours to get there. And finally, Neptune. Neptune, the last major planet, sits at about 30 ATU, 30 times the Earth-Sun distance. Light takes between 4 and 5 hours to reach Neptune from the Sun. 4 to 5 hours for light to travel from the Sun to Neptune, and here's what makes this hit even harder. The Voyager probes, the fastest human-made objects ever launched, have been flying for over 4 decades. And they've only just barely gotten past Neptune. We'll get to them in a moment. Because the outer planets aren't the edge of the solar system. They're not even close to the edge. They're just the beginning of how far out this thing actually goes. In 1977, humanity did something remarkable. We launched 2 spacecraft, Voyager 1 and Voyager 2, and we sent them on a journey that would take them further from Earth than anything human beings had ever built. They were designed to fly past the giant planets, collect data, take photographs, and keep going. And keep going they did. Voyager 1 has now been flying for over 47 years. 47 years of non-stop travel through the void. It's moving at about 17 kilometers per second. That's over 60,000 kilometers per hour. 60,000 kilometers per hour. Faster than anything humanity has ever launched. And where is it right now? Where is this object that has been screaming through space at 60,000 kilometers per hour for nearly half a century? It's about 24 billion kilometers from Earth. That sounds impressive, and it is. But here's the gut punch. That 24 billion kilometers, that staggering distance that took 47 years to cover at a speed that would circle the Earth in less than an hour, represents less than 0.07% of a single light year, less than 1/10 of 1%. Voyager 1, the farthest thing humanity has ever sent into space, is still basically right here, right next door, a rounding error. If the distance to the nearest star were a highway stretching across an entire continent, Voyager would be in the parking lot. It would barely have left the starting line. And that's after 47 years. If Voyager kept going at its current speed, which it essentially will, it would take about 70,000 years to reach the nearest star system. 70,000 years. Humanity's greatest achievement in space travel. Our fastest, most ambitious reach into the cosmos would take longer than all of recorded human history combined, multiplied by dozens, just to get to the next star over. That's not a failure. That's not a limitation of our technology exactly. That's just how big space is. It's telling you something about the scale of everything that comes next. And everything that comes next is so much bigger than this, it almost doesn't make sense to talk about it. Almost. Most people think the solar system ends at Neptune. Neptune, the last big planet, the outermost gas giant, the edge of the line. But that's not where the solar system ends. Not even close. Beyond Neptune, stretching out from about 30 ATU to roughly 50 ATU from the Sun, there's a region of space called the Kuiper Belt. And this is where things start to get interesting again. The Kuiper Belt is a vast, cold, dark ring of rocky and icy bodies orbiting the Sun way out past the major planets. It's where Pluto lives. And yes, I said lives, because Pluto isn't some lonely little outcast floating alone in the void. It's part of a neighborhood, a frozen, distant neighborhood, but a neighborhood nonetheless. The Kuiper Belt contains hundreds of thousands of objects. Some are small, just chunks of ice and rock a few kilometers across. But some are surprisingly large. Pluto itself is about 2,377 kilometers across, which actually makes it bigger than some things we used to call planets. And there are other objects out there of similar size. Eris, Makemake, Haumea. These are dwarf planets, worlds in their own right, drifting in the cold, dark beyond. Now, here's the thing about the Kuiper Belt that most people don't realize. It stretches out about 20 ATU beyond Neptune, 20 times the Earth-Sun distance, just sitting there between Neptune and deep space. That's not a thin ring, that's an enormous structure, and it completely changes your picture of what the solar system actually looks like. The solar system isn't just the Sun and 8 planets, it's the Sun, the planets, and then this massive frozen belt of debris and dwarf worlds that extends far, far beyond the last major planet. But even the Kuiper Belt isn't the real edge, not even close. Because beyond the Kuiper Belt, there's something even bigger. Something that stretches so far out, it borders on unimaginable. And we're about to go there. Okay, everything we've talked about so far, the moon, the sun, the planets, the Kuiper Belt, all of it, every single thing, is still inside a structure so enormous that most people have never even heard of it. It's called the Oort cloud, and it is the Sun's true boundary, the real edge of our solar system. Not Neptune, not the Kuiper Belt, the Oort cloud. And it is staggering. The Oort cloud is a vast, spherical shell of icy bodies that surrounds the entire solar system. Not a ring, not a disk, a shell. It wraps around everything, the Sun, all the planets, the Kuiper Belt, all of it, like a giant invisible bubble. And here's the part that should genuinely stop you in your tracks. The Oort cloud extends outward from the Sun to a distance of roughly 50,000 to 100,000 ATU. Let that sink in. 100,000 AU. Remember, 1 AU is the distance from the Earth to the Sun. The Oort cloud stretches out 100,000 times that distance. And here's the real kicker. 100,000 AU is roughly 1 light year, 1 full light year. The Sun's gravitational influence, the boundary of our solar system, stretches out about a light year in every direction. A light year, the unit we're about to use to measure everything beyond this point, the very first cosmic distance marker, the one that starts to bridge the gap between our solar system and the rest of the universe, is already part of our home. The Oort cloud is where comets come from, those streaks of light and ice that occasionally blaze across our sky, the ones that ancient civilizations saw as omens and prophecies. They start their journey from the Oort cloud. Something, usually the gravitational nudge of a passing star or another body, disturbs one of these icy objects and sends it tumbling inward on a long, slow fall toward the sun. That fall can take thousands of years. Thousands of years just to travel from the Oort cloud to the inner solar system. That's how far out it is. The solar system isn't a small, neat little system with a clear edge just past the last planet. It's a massive, sprawling structure that extends a full light year into space. And once you truly grasp that, the next thing we need to talk about, what a light year actually means, is going to hit completely differently. Okay, we need to stop here, because we've been throwing around a term for the last few minutes, light year. And most people hear that term, and their brain does one of two things. Either it treats it as just another big number, something impressive sounding but ultimately meaningless, or worse, it assumes a light year is a unit of time, like it's how long something takes. It's not. A light year is a distance, a measurement of how far something is, not how long something takes. And once you truly understand what that distance actually is, once you feel it in your gut, everything else in this video, every galaxy, every supercluster, every structure we're going to talk about for the next few hours, will land the way it's supposed to. So, let's break it down. Completely, second by second. Light travels at about 300,000 kilometers per second. In 1 second, a beam of light crosses a distance of 300,000 kilometers. That's like circling the entire Earth about 7.5 times. In 1 second. Now stretch that out. In 1 minute, light travels about 18 million kilometers. In 1 hour, it covers about 1 billion kilometers. In 1 day, about 26 billion kilometers. You can already feel the numbers getting uncomfortable, right? Keep going. In 1 year, light travels about 9.46 trillion kilometers. 9.46 trillion. That's 1 light year. That is, the distance light covers in 1 full year of non-stop, unbroken travel at the fastest speed anything in the universe can move. And here's how to feel that. Remember Voyager 1? The spacecraft that's been flying for 47 years at 60,000 kilometers per hour? It has covered less than 1% of a single light year. 1% in 47 years. So, a light year isn't just big, it's incomprehensibly, almost unfathomably big. It makes the entire solar system, everything we just traveled through, everything we mapped out from Earth to the Moon to Neptune to the Oort cloud, it makes all of that look like a single step. One tiny step on a journey that hasn't even started yet. Because the nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. And that's our closest neighbor. That's the first stop, and we are nowhere near ready to get there. But we will get there in this video, because from here on out, light-years are the unit, and the numbers are about to get very, very large. Here it is, the first stop beyond our solar system, the nearest star to our Sun. It's called Proxima Centauri, and it sits 4.24 light-years away. Now, we just spent a lot of time making sure you understood what a light-year actually means. So let's use that understanding right now. Because 4.24 light-years sounds almost modest after everything we've been through. It's not. It's terrifying. Let's put it in terms of travel time. With our current best technology, the fastest spacecraft we've ever built, Voyager 1. Remember, it's been flying for 47 years and has covered less than 1% of a single light-year. At that speed, it would take Voyager roughly 70,000 years to reach Proxima Centauri. 70,000 years. That's longer than all of recorded human civilization. We didn't even have agriculture 70,000 years ago. Now, what if we could do better? What if, someday, we built something dramatically faster? Let's say we cracked the code and built a spacecraft that could travel at 1% of the speed of light. 1%. That would be an engineering achievement beyond anything we can currently imagine. And at that speed, it would still take over 400 years to reach Proxima Centauri. 400 years. Your great-great-great-great-great-grandchildren might see it arrive. And even the most optimistic science fiction level fantasies, traveling at 10% of light speed, would still take over 42 years for a one-way trip. You'd launch. You'd spend your entire adult life in transit. And maybe, if everything went perfectly, you'd arrive at the nearest star before you died. That's our closest neighbor, the very first star beyond our own. And it is profoundly, deeply, uncomfortably far away. We are not surrounded by stars. We are isolated, sitting in a pocket of space where the nearest other sun is a distance so vast that crossing it is, for all practical purposes, impossible with anything we can currently build, or even reasonably imagine building. Proxima Centauri is close, cosmically speaking. Astronomers call it a neighbor. But in every way that actually matters to human beings, it might as well be on the other side of an uncrossable ocean. And that ocean only gets wider from here. But here's something most people don't know about Proxima Centauri. It's not alone. It's part of a system of 3 stars, all bound together by gravity, performing a slow gravitational dance that's been going on for billions of years. And that system is called Alpha Centauri. Now, when you hear Alpha Centauri, you might picture a single star. It's not. It's 3. Alpha Centauri A and Alpha Centauri B are 2 stars that orbit each other relatively closely. They're both similar in size to our Sun. A is slightly bigger, slightly brighter, slightly hotter. B is a little smaller, a little cooler. They're orbiting each other at a distance of roughly 23 AUU, which sounds like a lot, but remember, we just traveled through a solar system that stretches a light-year across. 23 AUU is practically next door by comparison. These 2 stars have been dancing around each other for billions of years. If you could watch them from far enough away, you'd see a slow, elegant binary waltz, 2 suns circling each other over decades. Their orbital period is about 80 years. So in one human lifetime, you could watch them complete one full loop. And then there's Proxima Centauri, the one we just talked about, the nearest star to our Sun, is actually the 3rd member of this system, but it sits much further out. It orbits Alpha Centauri A and B at a distance of roughly 13,000 HRU. That's an enormous orbit. It takes Proxima about 500,000 years to complete one loop around its 2 companion stars. 500,000 years for one orbit. So when astronomers say our nearest neighbor is 4.24 light-years away, they're really talking about a whole system, a gravitational family of 3 stars, bound together across vast distances, moving through space as one unit. And here's what makes this hit even harder. This 3-star system, this nearest cosmic neighborhood, is still sitting in an ocean of emptiness. The next star beyond Alpha Centauri is further away still, and the one after that even further. The stars are not clustered together. They are scattered. Lonely suns drifting through an almost infinite void. Alpha Centauri is proof of that. Even our closest neighbor turned out to be a family of three, and they're still alone out there, just like we are. Let's zoom out a little. Instead of looking at just the nearest star, let's look at everything within 100 light years of the Sun. Our stellar neighborhood, the cosmic equivalent of our block, our local area, the region of space we could theoretically map and study in some detail. And here's what you find when you actually chart it out. Emptiness. Stunning, breathtaking emptiness, punctuated by a few lonely stars scattered across an enormous volume of space. Within 100 light years of us, astronomers have identified roughly 300 to 400 stars. That sounds like a lot until you think about what 100 light years actually means. That's a sphere of space so enormous that light itself takes 100 years to cross it from one side to the other. And inside that sphere, there are only a few hundred suns. If you could somehow shrink that entire 100 light-year neighborhood down to the size of a basketball, each star would be smaller than a grain of dust, and they'd be separated by gaps you couldn't see. The Sun is not in a crowded part of the galaxy. It's not near a dense cluster of stars. It's not in a busy cosmic intersection. It's out here, in a relatively quiet stretch of the Milky Way, with a handful of neighbors spread out over distances that would take thousands of years to cross, even at light speed. Some of these nearby stars are interesting. Barnard's star, about 6 light-years away, is one of the fastest-moving stars across our sky. Sirius, at 8.6 light-years, is the brightest star you see at night, and it's a binary system, 2 stars orbiting each other. Tau Ceti, about 12 light-years out, is one of the stars scientists have looked at most closely for signs of planets that might support life. But none of them are close. Not really. Not by any standard that would make travel between them possible with anything we can currently build. The stellar neighborhood is vast. It is sparse. And it is by every measure lonely. We live in a quiet corner of the galaxy, surrounded by empty space, with a few distant suns for company. And that quiet corner, as we're about to see, is itself just a tiny piece of something incomprehensibly larger. Everything we've talked about so far, every star, every planet, every single thing in the universe, came from the same place. Clouds, enormous, mind-bending clouds of gas and dust floating in space. They're called nebulae, and they are where stars are born. Now, when I say cloud, I don't want you picturing something fluffy and small. These are not clouds, like the ones you see in the sky on a rainy day. These are structures so vast that a single nebula can stretch for hundreds of light years across. Hundreds of light years. Remember, light takes over 4 years just to reach the nearest star. A single nebula can be dozens or even hundreds of times wider than that. It's not a cloud. It's a continent of gas drifting through the void. Inside these nebulae, the gas is mostly hydrogen, the simplest and most abundant element in the universe. Mixed in with that is helium, dust, and traces of heavier elements left behind by stars that lived and died billions of years ago. And most of the time, this gas just floats. It drifts. It doesn't do much of anything. But sometimes, something triggers a change, a shockwave from a nearby supernova, the gravitational pull of a passing star, some disturbance that compresses a small region of the cloud, just enough to tip the balance. And when that happens, gravity takes over. The compressed gas starts pulling in more gas. More mass means more gravity. More gravity means more compression. It's a runaway process, a slow, magnificent collapse that can take millions of years to play out. But at the end of it, a star is born, a new sun igniting for the first time, fusing hydrogen into helium at its core, blazing to life inside the very cloud that created it. This is happening right now. As we speak, in nebulae scattered across the Milky Way, new stars are being born. Some of them will have planets. Some of those planets might, given enough time and the right conditions, develop life. The nebulae are the factories of the universe. And their scale, their sheer enormity, dwarfs everything we've looked at so far. We're leaving the solar system behind now. We're entering the realm where the distances and the structures are almost beyond words. You've seen it. You might not have known what you were looking at, but you've seen it. On a clear night, if you find the constellation Orion, the Hunter, and you look at the three stars that form his belt, then look just below them, there's a faint, hazy smudge. That smudge is the Orion Nebula, and it is one of the most extraordinary things in the sky. The Orion Nebula sits about 1,344 light-years from Earth. That's already a staggering distance. But what makes it remarkable isn't just how far it is. It's what's happening inside it. The Orion Nebula is an active stellar nursery, a massive cloud of gas and dust where thousands of stars are currently in the process of being born. Some have already ignited. Young, hot, blazing, newborn stars, many of them only a few million years old. Babies, by stellar standards. Others are still collapsing, still gathering mass, still on their way to becoming suns. The Orion Nebula stretches across roughly 1,344 light-years, but the brightest, most active region, the heart of the factory, spans about 24 light-years across. 24 light-years. That's 6 times the distance from our Sun to the nearest star, all packed into a single region of active star formation. Inside that region, astronomers have identified thousands of young stars. Some are massive, many times the size of our Sun, burning hot and bright and blue. Others are small and cool and dim, red dwarfs that will burn for trillions of years long after the Sun has died. The Orion Nebula is showing us something profound. It's showing us that star formation isn't rare. It's not some quiet, isolated event that happens once in a blue moon. It's an industrial process, a massive, ongoing, churning factory where the universe is constantly, actively making new suns. And some of those suns will have planets. And some of those planets will orbit at just the right distance for liquid water to exist. The Orion Nebula is 1,344 light-years away, utterly unreachable, but it's visible to the naked eye, a fuzzy patch of light that, if you knew what you were looking at, would stop you cold, because you're looking at the future. You're looking at stars being born right now, tonight, as you stare up at the sky. Stars don't always drift alone through the galaxy. Sometimes they travel in groups, hundreds of them, thousands of them, born together from the same cloud of gas, moving through space as a pack. These are called star clusters, and they come in 2 very different flavors. The first type is called an open cluster. These are relatively young groups of stars, usually a few hundred to a few thousand stars, all born from the same nebula at roughly the same time. They're spread out, loosely bound by gravity, and slowly drifting apart over millions of years. The most famous example is the Pleiades. You've seen them, that tight little group of blue stars in the constellation Taurus, the Seven Sisters, as they're sometimes called, though there are actually more than 7 if you look closely. The Pleiades are only about 100 million years old. Babies. They were all born from the same cloud of gas, and they're still traveling together, though gravity is slowly pulling them apart. In another few 100 million years, they'll drift away from each other and disappear into the background stars. Open clusters are cities in the void, bright, young, temporary gatherings of stars that will eventually dissolve. But then there are globular clusters, and these are something else entirely. Globular clusters are ancient. We're talking 10 to 13 billion years old. Dense, spherical collections of stars, hundreds of thousands or even millions of stars packed tightly together, all orbiting a common center. Omega Centauri is the largest globular cluster visible from Earth. It contains roughly 10 million stars. 10 million stars, all bound together in a single gravitational structure, visible as a single bright point if you don't know what you're looking at. It sits about 17,000 light-years away. And here's what makes globular clusters so striking. They are ancient relics. They formed in the very early universe, billions and billions of years ago, and they've been orbiting the Milky Way ever since. They are some of the oldest structures in our galaxy. Stars within globular clusters are packed so tightly that if you lived on a planet inside one, your night sky wouldn't be dark. It would glow. Thousands of stars close enough to cast visible light, turning the darkness into a permanent dim twilight. Clusters, open and globular, are the cities scattered across the galaxy, and the galaxy itself, the structure that holds them all, is about to come into full view. All right, here it is, the big one, the structure we've been building towards this entire time, the Milky Way, our home galaxy. And before we go any further, I need you to understand what it actually looks like. Not the way it looks from Earth, that pale band of light stretching across the sky. I mean its real shape, its true structure. Because the Milky Way is a disk, a flat, spinning disk of stars, gas, dust, and dark matter. Imagine holding a dinner plate out in front of you, thin in the middle, wide across. That's the shape. Now make that plate 100,000 light-years across, 100,000 light-years from one edge to the other, and make it about 1,000 light-years thick in most places, though the central bulge, the bright hub at the center, puffs out to maybe 10,000 to 12,000 light-years thick. That's the Milky Way, a colossal spinning disk of matter containing somewhere between 100 billion and 400 billion stars. The exact number is genuinely hard to pin down. Counting stars in a galaxy you're inside of is like trying to count all the fish in the ocean while swimming in it. You can see some. Most are hidden, obscured by dust, by distance, by other stars blocking the view. But even the low estimate, 100 billion stars, is a number so enormous it breaks the brain a little. 100 billion. If you counted one star per second, without stopping, without sleeping, it would take you over 3,000 years to count them all. And that's the low end. The Milky Way isn't a ball. It's not a cloud. It's a disk. A flat, structured, organized disk with spiral arms curling outward from a central bulge. And we live inside it, not on the surface, not looking at it from the outside, inside, which is actually one of the reasons it took us so long to figure out what it looked like. You can't see the shape of something you're buried in the middle of, but astronomers have pieced it together over centuries of observation, and the picture they've built is breathtaking. We live in a galaxy that is genuinely, impressively, undeniably massive, and we're about to find out exactly where inside it we sit. If the Milky Way were a city, and every star were a building, the sun would have a very specific address, and that address is not in the center. It's not on the edge. It's somewhere in between, somewhere ordinary, somewhere you'd describe as the suburbs. The sun sits about 26,000 light-years from the center of the Milky Way. 26,000 light-years. That's roughly a quarter of the way in from the edge, give or take. Not central, not peripheral, just middle. And the sun doesn't sit in one of the Milky Way's major spiral arms. Those grand, sweeping structures that give the galaxy its shape, we're not in one of those. We're in something smaller, a minor arm, a spur. It's called the Orion Arm, or sometimes the Orion Spur, named because the constellation Orion, as seen from Earth, lines up roughly with the direction this arm extends. The Orion Arm is about 3,500 light-years long and roughly 1,500 light-years wide. By Milky Way standards, that's small. It's a short branch connecting two of the galaxy's largest spiral arms, the Sagittarius Arm and the Perseus Arm. We live on a minor road between two highways, and here's what makes this address interesting. It's not interesting. That's the point. The sun is not in a particularly dense region of the galaxy. It's not near a major stellar nursery. It's not close to the galactic center where everything is packed tight and chaotic and violent. It's out here in a relatively quiet stretch where the density of stars is moderate, where supernova explosions are rare enough that they don't sterilize the local neighborhood every few million years, where conditions have been stable enough for billions of years for a rocky planet to form, cool down, and develop life. We live at an ordinary address in an ordinary part of an extraordinary galaxy, and that ordinariness might be exactly why we're here. The galactic center is a brutal, radiation-soaked, chaotic environment. Life as we know it probably couldn't survive there. Our quiet little corner of the Orion Arm might be one of the calmest, safest places in the entire Milky Way. Ordinary has never been so valuable. Here's a fact that should genuinely mess with your sense of time. The sun is moving. Right now, as you sit here, the sun and everything attached to it, Earth, the moon, the entire solar system, is hurtling through space at about 220 kilometers per second. That's nearly 800,000 kilometers per hour, faster than anything human beings have ever built. And it's been doing this for billions of years. The sun is orbiting the center of the Milky Way. Just like Earth orbits the sun, and the moon orbits Earth, the sun is locked in a slow, massive orbit around the galactic center. And here's where the scale really hits. One complete orbit, one full loop around the Milky Way, takes the sun roughly 225 to 250 million years. That's called a galactic year. One galactic year, 225 million Earth years to go around once. Let's put that in perspective against something you might actually understand. The dinosaurs went extinct about 66 million years ago. That means the sun hasn't even completed 1/3 of a single galactic orbit since the dinosaurs disappeared. When the dinosaurs were alive, the sun was in a completely different part of the galaxy than it is now. When the first complex life appeared on Earth, over 500 million years ago, the sun had completed maybe 2 full galactic orbits since then. 2 laps in over 500 million years. The sun has completed roughly 20 to 25 full orbits around the Milky Way in the entire history of Earth. 25 laps in 4.5 billion years. That's how slow this orbit is. And here's what makes it even more striking. During each one of those orbits, the sun passes through different regions of the galaxy. Some regions are denser, some are quieter, some have more radiation. The sun's journey around the Milky Way has taken it through different cosmic environments over the billions of years, and those environments have changed the conditions on Earth in ways we're still trying to understand. We don't just live on a planet orbiting a star, we live on a planet orbiting a star that is itself orbiting a galaxy. Motion inside motion, and the outermost loop, the galactic orbit, takes 250 million years to complete. The universe operates on timescales that make human history look like a single heartbeat. At the very center of our galaxy, right at the heart of the Milky Way, there is a monster, a supermassive black hole called Sagittarius A, and it has been sitting there at the core of our home for billions of years. Now, before you panic, let me be clear. It is not a threat to us. It is 26,000 light-years away. It has no meaningful gravitational influence on the solar system. It is not coming for us, but it is extraordinary, and understanding it changes how you see the Milky Way. Sagittarius A has a mass of about 4 million times the mass of our Sun. 4 million suns compressed into a single object so dense that nothing, not light, not information, not anything, can escape once it crosses the boundary. The event horizon, the point of no return, is surprisingly small for something so massive. The entire event horizon of Sagittarius A is only about 12 million kilometers across. That sounds big until you remember that 12 million kilometers is less than 1/10 of the distance from the Earth to the Sun. A black hole containing 4 million suns and its point of no return fits inside our solar system. That's how insane black hole physics is. For decades, Astronomers knew Sagittarius A was there. They could see its effects. Stars near the galactic center orbit at incredible speeds, whipping around invisible mass at velocities that only make sense if there's something enormously heavy at the center. One star, called S2, orbits Sagittarius A in just 16 years, looping around at speeds of over 3% of the speed of light. 3% of light speed, around something you can't see. Then, in 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. The first time in human history we actually saw the shadow of the black hole at the center of our own galaxy. It looked like a fuzzy orange ring of light with a dark center. Simple, almost modest. But that image represented decades of work, hundreds of scientists, and telescopes spread across the entire Earth working together as one. Sagittarius A is the anchor of the Milky Way, the gravitational center around which everything else, every star, every nebula, every cluster, every one of the hundreds of billions of stars in our galaxy is ultimately orbiting. It is the heart of our home, and it is a black hole. We've been living out here in the suburbs. Quiet, spacious, relatively empty. But at the very center of the Milky Way, things are completely, radically different. And I mean completely. The galactic center is a place that would be almost unrecognizable if you could somehow stand on a planet there and look up at the sky. Because the center of the Milky Way is packed, densely, overwhelmingly, almost incomprehensibly packed with stars. The structure at the heart of our galaxy is called the galactic bulge. It's a thick, roughly spherical swelling of stars that sits at the very center of the disk, and it is enormous. The bulge stretches about 10,000 to 12,000 light-years across and contains billions upon billions of stars, not spread out like they are out here in the arms, crammed together, packed so tightly that the density of stars near the galactic center is thousands of times higher than it is where the sun sits. If you lived on a planet near the center of the Milky Way, there would be no true darkness at night. The sky would glow. Stars would crowd every direction, so close and so numerous that constellations as we know them would be meaningless. The light would never fully go away. Now contrast that with where we live. Out here in the Orion Arm, the stars are scattered, lonely, separated by years and years of empty space. The density of stars around the sun is maybe a few stars per cubic light-year. Near the galactic center, that number jumps by orders of magnitude. It's like comparing a quiet country road to the most crowded highway intersection in the world. And the bulge isn't just bright. It's old. Most of the stars in the galactic bulge are ancient, red and orange giants that have been burning for billions and billions of years. They formed early in the galaxy's history, back when gas was dense and star formation was rapid. The bulge is a relic, a fossil record of the Milky Way's earliest, most violent era of star creation. Out here in the arms, stars are still being born. New, young blue stars ignite in nebulae and nurseries. But at the center, the frantic pace of creation has slowed. The bulge just glows, ancient and dense, a crowded heart beating at the core of everything we call home. Here's something that might surprise you. The Milky Way doesn't end at the disk, the flat, spinning structure we've been talking about, the one that's 100,000 light-years across, with all the spiral arms and the stars and the nebulae. That's not the whole galaxy, not even close. Surrounding the disk, wrapping around it like an enormous invisible shell, is something called the galactic halo, and it is where most of the Milky Way's mass actually lives. The halo is a vast, roughly spherical region that extends far beyond the boundaries of the visible disk. How far? Astronomers estimate it stretches out to maybe 200,000 light-years or more from the center of the galaxy. Twice the diameter of the disk, maybe more, and it is mostly invisible. You can't see it, not with your eyes, not easily with telescopes. Because the halo is not made of the bright young stars that light up the spiral arms. It's made of two things, old stars and dark matter. The old stars in the halo are ancient. Some of them are among the oldest objects in the entire universe, over 13 billion years old. They're dim, cool red dwarfs and ancient giants that drifted out here billions of years ago, or were captured from smaller galaxies that the Milky Way consumed. They form loose, diffuse clouds called globular clusters, which we talked about earlier, scattered through the halo like embers drifting in the dark. But the old stars are only a small part of what's out here. The real mass, the dominant component of the halo, is dark matter, and we're going to talk about dark matter in detail in just a moment. But for now, here's what you need to understand. The halo is where the bulk of the Milky Way's gravitational muscle comes from. The disk, the visible part, the part with all the stars and gas and light, is actually a relatively small fraction of the galaxy's total mass. The halo dwarfs it. It holds the whole structure together. Without the halo, without all that invisible mass wrapping around the disk, the Milky Way wouldn't work. The stars in the arms would fly apart. The galaxy would dissolve. The halo is the skeleton, the invisible framework that makes the Milky Way possible. And we can barely see it. All right, here's where things get genuinely strange. We've been talking about the Milky Way as if it's mostly made of stars, planets, gas, dust, stars, the stuff we can see, the stuff we can point to and say, there, that's matter, that's real. But here's the truth. That stuff, all of it, everything you've ever touched, everything you've ever seen, every star, every planet, every galaxy, every single visible thing in the entire observable universe, makes up only about 5% of the total mass and energy in the cosmos. 5%. The rest, most of it, about 27%, is something called dark matter, and we have absolutely no idea what it is. Let me say that again. We don't know what dark matter is. We have never directly detected a single particle of it. We have never seen it, touched it, or interacted with it in any direct way. And yet without it, the Milky Way and every other galaxy in the universe would not exist. Here's how we know it's there. Galaxies spin. Stars orbit the galactic center, and they do it at specific speeds. If a galaxy were made only of the visible matter we can see, the stars on the outer edges should be moving slower than the stars near the center. That's just basic gravity. The further you are from the center of mass, the less gravitational pull you feel, the slower you move. But that's not what astronomers observe. Stars on the outer edges of galaxies move just as fast as stars closer to the center, sometimes faster. The only way to explain that is if there's a massive amount of invisible matter spread throughout the galaxy, providing extra gravitational pull that we can't see. That invisible matter is dark matter. In the Milky Way, dark matter makes up roughly 80 to 85% of the total mass. 80 to 5%. The stars, the gas, the planets, everything visible is just the tip of the iceberg. The iceberg itself is made of something we cannot see and do not understand. Dark matter doesn't interact with light. It doesn't emit light. It doesn't absorb light. It just exists, pulling on everything with gravity, holding galaxies together, forming the invisible scaffolding on which all visible matter is built. It's the most dominant substance in the universe, and it remains one of the deepest mysteries in all of physics. The Milky Way is not mostly stars, it's mostly dark matter, and we have no idea what that means. The Milky Way isn't alone out here in space. It has company, a whole entourage of smaller galaxies orbiting around it, caught in its gravitational grip, circling our galaxy like moons circle a planet. And there are a lot of them. More than 50 known satellite galaxies have been identified orbiting the Milky Way. 50 small galaxies, each one a collection of millions or even billions of stars, all trapped in orbit around us. The most famous of these are the Magellanic Clouds, the Large Magellanic Cloud, and the Small Magellanic Cloud. If you're in the southern hemisphere, you can actually see them with your naked eye. They look like fuzzy patches of light, two small smudges hanging in the sky near the Southern Cross. But they're not smudges, they're galaxies. The Large Magellanic Cloud contains roughly 10 billion stars and stretches about 14,000 light-years across. The Small Magellanic Cloud is smaller, maybe a few billion stars, about 7,000 light-years across. They're about 160,000 and 200,000 light-years from Earth, respectively. Close by galactic standards. And they're both on a slow, inexorable journey toward the Milky Way. Eventually, billions of years from now, the Milky Way's gravity will pull them in completely. They'll be consumed, torn apart, their stars absorbed into our galaxy. It's already happened before. The Sagittarius Dwarf Elliptical Galaxy is being eaten right now. It's a small galaxy that passed too close to the Milky Way and is currently being ripped apart by tidal forces. Its stars are being stretched into a long stream, a ribbon of stolen suns wrapping around our galaxy. We've already swallowed dozens of galaxies like it over the course of billions of years. The Milky Way is a gravitational landlord, a massive spiral that sits at the center of its own little empire, pulling smaller galaxies into orbit, and eventually consuming them. Every large galaxy does this. It's how they grow. The Milky Way's satellite galaxies are not just neighbors, they're future ingredients. Pieces of a puzzle that will eventually be folded into the Milky Way itself, adding their stars and mass to our galaxy over the coming billions of years. The Milky Way didn't get this big by accident. It ate its way here. Here's something that should genuinely change how you think about the future. The Milky Way is on a collision course with another galaxy. A big one, the biggest galaxy in our immediate neighborhood. It's called Andromeda, and it is heading straight for us. Andromeda, also known as M31, sits about 2.5 million light-years away, 2.5 million light-years. That's roughly 25 times the diameter of the Milky Way itself. Just to give you a sense of the distance between us and our nearest large neighbor, Andromeda is bigger than the Milky Way. It contains roughly 1 trillion stars, compared to our few hundred billion. It's wider, more massive, and from a distance it would be an imposing sight if you could see it clearly. And it is falling toward us. Right now, the two galaxies are closing the gap at about 110 kilometers per second, and in roughly 4.5 billion years, they will meet. Now, I said collision, and that word makes most people picture something violent. Two massive objects smashing into each other. Destruction, fire, the end of everything. But here's the thing that makes this so fascinating. It won't look anything like that, because galaxies are almost entirely empty space. Remember how we talked about the solar system being mostly nothing? The spaces between stars are even more brutal. Stars are so incredibly far apart that when two galaxies pass through each other, the chance of any two stars actually colliding is essentially zero. Not small, essentially zero. The two galaxies will interpenetrate, pass through each other like two clouds of smoke drifting into one another. They'll gravitationally distort each other. Stars will be flung into wild new orbits. The spiral arms of both galaxies will be completely disrupted, but almost nothing will physically crash. Over the course of several billion years, the two galaxies will pass through each other, fall back together, pass through again, and eventually settle into a single large elliptical galaxy. Some astronomers have nicknamed the result Milkomeda or Milkdromeda. It'll be one of the larger galaxies in the local neighborhood, but even that won't be particularly special on a cosmic scale. It's just what happens when two galaxies meet. And ours are about to zoom out, past the Milky Way, past Andromeda, And you start to see something bigger, a neighborhood. A collection of galaxies, all bound together by gravity, all moving through space as a loose community. It's called the local group, and it is our galactic community. The local group contains over 50 known galaxies, 50 worlds unto themselves, each one containing millions or billions or even trillions of stars, all gravitationally connected, all part of the same cosmic neighborhood. But here's the thing, it is not a crowded neighborhood. The local group stretches across about 10 million light-years. 10 million. That's 100 times the diameter of the Milky Way, and most of that space is empty. The galaxies are spread out across that enormous volume with vast gulfs of nothing between them. And the group is not made up of equals. It's dominated by two galaxies, ours, the Milky Way, and Andromeda. Those two are the giants, the heavyweights. Everything else in the local group is small by comparison. Triangulum, the third largest spiral, contains only about 40 billion stars, less than half what the Milky Way has. And then there are the dwarfs, dozens of them. The Magellanic Clouds, the Sagittarius Dwarf, Leo I, Leo II, Draco, Sculptor, Fornax, each one a tiny galaxy, a few billion stars at most, many of them just a few million. Satellites orbiting the two big spirals or drifting loosely between them. The local group is essentially a two-king kingdom with dozens of small villages scattered around. Andromeda and the Milky Way run the show. Everything else is along for the ride. And here's what's about to happen to all of it. Over the coming tens of billions of years, the local group will collapse inward. The expansion of the universe will slow its effect on this tightly bound collection of galaxies. Andromeda and the Milky Way will merge. And eventually, over an enormous span of time, the entire local group will condense into a single massive structure. All those galaxies, all those stars, all that history folded into one. But that's the future. Right now, the local group is just the beginning of something even larger, and we're about to find out what that something is. The local group isn't floating alone in the void. It's falling. Right now, the entire local group, the Milky Way, Andromeda, all 50-plus galaxies, is being pulled towards something enormous, something called the Virgo cluster, and it is the nearest major hub of galaxies in the universe. The Virgo cluster sits about 54 million light-years from Earth. 54 million. That's already a distance so vast, it barely registers. And it contains somewhere between 1,000 and 2,000 galaxies. 1,000 galaxies. All packed into a single cluster, all bound together by gravity, all orbiting a common center. And not small galaxies either. Some of the galaxies in the Virgo cluster are enormous. M87, which we'll talk about more later, is a supergiant elliptical galaxy at the heart of the cluster containing about 1 trillion stars and a black hole. 6.5 billion times the mass of the Sun, M84, M86, NGC 4472. These are massive galaxies, many of them far larger than the Milky Way. If you could somehow transplant the solar system into the Virgo cluster, the Milky Way would be just another medium-sized spiral. Nothing special. Lost in a crowd. Now here's where the concept of scale really starts to shift. The Virgo cluster is not just a cluster. It's the gravitational heart of something much bigger. The local group, our quiet little neighborhood of 50 galaxies, is part of a supercluster. A structure so large it contains not just individual galaxies, but entire clusters of galaxies. The Virgo supercluster, as it's called, contains at least 100 galaxy clusters and groups, including the Virgo cluster itself at its center. It spans roughly 110 million light-years across. 110 million light-years. The Milky Way, at 100,000 light-years across, could fit across the Virgo supercluster over 1,000 times. We went from being one galaxy in a group of 50 to being one galaxy in a supercluster containing trillions of stars across hundreds of galaxy clusters. The scale just jumped by orders of magnitude. And even this, the Virgo supercluster, turns out to be just one piece of something even larger, something that was only discovered about a decade ago. And it's about to blow your mind. In 2014, a team of astronomers did something remarkable. They mapped the flow of galaxies through space. Not just where galaxies are, but where they're moving. Which direction? How fast? And when they plotted all of that motion on a map, a shape emerged. An enormous structure defined not by the galaxies themselves, but by the gravity pulling them all toward a common center. They named it Laniakea. The name comes from Hawaiian. It means immeasurable heaven, and that name is earned. Laniakea is a supercluster of superclusters. It contains roughly 100,000 galaxies. 100,000 galaxies, including our own Milky Way, all part of the same gravitational structure. It stretches across about 520 million light-years. 520 million. Let that land for a second. 520 million light-years. The Milky Way is 100,000 light-years across. Laniakea is 5,200 times wider. If you shrank Laniakea down so that the Milky Way was the size of a grain of sand, Laniakea itself would be the size of a large room. We went from a grain of sand to a room. That's the jump in scale. Inside Laniakea, there are superclusters. The Virgo supercluster, which we just talked about, is just one of them. There are others, dozens of them, each one containing hundreds or thousands of galaxies, each one spanning hundreds of millions of light-years. And all of them, every single one, are part of Laniakea. They're all falling inward, pulled by the combined gravity of everything in the structure, moving toward a region called the Great Attractor, a concentration of mass so enormous that thousands of galaxies across millions of light-years are being drawn toward it. The Milky Way is part of that motion. Right now, we are falling toward the Great Attractor, along with everything else in Laniakea. And here's what makes Laniakea so striking. Before 2014, we didn't know it existed. Not really. We knew about the Virgo supercluster. We knew about some of the galaxy clusters inside it. But the full picture, the true shape and extent of our cosmic home, was only revealed when someone thought to map not just where galaxies sit, but where they're going. Laniakea is our cosmic address, the largest known structure that contains us. And it is immeasurably, magnificently vast. Here's a question that sounds simple but isn't. How big is the universe? The answer depends on what you mean. Because there are two universes. The actual universe, which might be infinite, which might go on forever in every direction, and the observable universe, the part we can actually see. And the observable universe has a very specific size. It's about 93 billion light-years across. 93 billion. Now, you might think that number should be about 27.6 billion, because the universe is 13.8 billion years old, so light should have had time to travel 13.8 billion light-years in any direction, making the observable universe about 27.6 billion light-years across. Logical. Makes sense, but it's wrong. And the reason it's wrong is one of the most mind-bending ideas in all of cosmology. The universe is expanding. Space itself is stretching. It's not that galaxies are flying apart through space like shrapnel from an explosion. Space itself, the fabric of everything, is getting bigger. So a galaxy that emitted light 13 billion years ago has moved much, much farther away during the time that light has been traveling toward us. By the time that light reaches us, the galaxy might now be 46 billion light-years away. That's why the observable universe is 93 billion light-years across. It's the maximum distance from which light has had time to reach us, accounting for all that stretching. But here's the crucial thing to understand. The edge of the observable universe is not a wall. It's not a physical barrier. It's not the edge of anything real. It's a horizon, like the horizon you see when you look out at the ocean. You can't see beyond it, but there's more ocean on the other side. The observable universe is just the limit of what we can see, given how long the universe has existed and how fast light travels. Beyond that horizon, the universe almost certainly continues. How far? We don't know. It might go on forever. It might be infinite. We have no way to find out, because by definition, we can never see beyond the observable boundary. We are trapped inside a bubble of visibility, a sphere 93 billion light-years across, and everything beyond it is forever hidden from us. And even inside this bubble, the Milky Way is one galaxy among an estimated 2 trillion others. Galaxies are not scattered randomly through space. If they were, if you plotted their positions on a map, you'd get something that looked like pepper shaken onto a white tablecloth. Evenly distributed, uniform. But that's not what the universe looks like. Not even a little bit. When astronomers actually mapped the positions of galaxies across enormous distances, what they found was something stunning. A pattern, a structure, a cosmic web. Galaxies don't just float in empty space. They cluster along filaments, long, thin threads of matter, stretching across hundreds of millions of light-years. These filaments connect at nodes where massive galaxy clusters sit. And between the filaments, between the nodes, between all the matter, are voids, enormous, almost empty regions of space, where very few galaxies exist at all. The largest of these voids can be over 1 billion light-years across, 1 billion light-years of almost nothing. And the largest of the filaments and structures, they are almost beyond comprehension. The Hercules Corona Borealis Great Wall is the largest known structure in the observable universe. It is a galactic filament, a long chain of galaxy clusters and superclusters, stretching across roughly 10 billion light-years. 10 billion. The Milky Way is 100,000 light-years across. The Great Wall is 100,000 times larger. If you traveled at the speed of light, non-stop, it would take you 10 billion years to cross it. That's more than 70% of the age of the universe itself. And here's what makes this structure genuinely disturbing to cosmologists. According to our best models of how the universe formed, structures this large shouldn't exist. The universe is only 13.8 billion years old. Gravity works slowly. It takes time for matter to clump together. Our simulations predicted that the largest structures should be no more than about 1.2 billion light-years across. The Great Wall is roughly 10 times larger than that. Its existence suggests that either our models are incomplete or the universe formed in ways we don't fully understand yet. The cosmic web, the filaments, the voids, the walls, this is the largest scale structure in the universe. And inside it, inside one filament, in one supercluster, in one galaxy cluster, in one small group of galaxies, sits the Milky Way. One thread in a web that stretches across the entire observable universe. And the web itself is almost incomprehensibly vast. We've talked about empty space a lot tonight. The emptiness between planets, the emptiness between stars, the emptiness between galaxies. But none of that, none of it, prepares you for the voids, the truly cosmic voids. Because at the largest scales, the universe isn't mostly matter. It isn't mostly galaxies. It isn't mostly anything you can see, or point to, or name. It is mostly nothing. Vast, staggering, almost incomprehensible regions of space where almost nothing exists at all. These are called cosmic voids, and they are enormous. The largest known void, the KBC void, stretches roughly 2 billion light-years across. 2 billion. Think about what that means for a second. The entire observable universe is 93 billion light-years across. A single void inside it is 2 billion light-years wide. If you were somehow placed at the center of the KBC void and looked out in any direction, the nearest significant concentration of galaxies would be about 1 billion light-years away. 1 billion light-years of near emptiness in every direction. The entire Milky Way, at 100,000 light-years across, could fit across that void 20,000 times. 20,000 Milky Ways, end to end, and you still wouldn't have crossed it. And here's the thing that really puts it in perspective. Voids like this make up about 80% of the universe's volume. 80%. The vast majority of space, the overwhelming majority of the universe, is empty. The galaxies, the superclusters, the filaments, all the matter, all the structure, all the stuff, it occupies only about 20% of the total volume. We live in the matter. We live in the stuff. But the stuff is the exception, not the rule. The universe is an ocean, a cold, dark, almost infinite ocean. And the galaxies are islands, tiny specks of matter floating in an endless sea of nothing. The Milky Way, for all its hundreds of billions of stars, for all its magnificent structure, is one of those specks drifting in a void so vast that even the word enormous doesn't come close. The universe is mostly empty, at every scale. From the space between atoms to the space between galaxies, emptiness is the default. Matter is the anomaly, and we, somehow, improbably, are made of it. 2 trillion. That's the number. 2 trillion galaxies in the observable universe. 2, followed by 12 zeros. And I want you to really sit with that for a moment, because most people hear that number and it just slides off. It doesn't stick. It doesn't feel real. So let's make it feel real. If every single galaxy in the observable universe were represented by a single grain of sand, you would need enough sand to fill several Olympic-sized swimming pools. The Milky Way would be 1 grain. 1 grain in several swimming pools full of sand. Indistinguishable. Now, how did astronomers arrive at that number? Because for a long time, the estimate was much lower, around 200 billion. 200 billion galaxies. That was the standard number for years. And then, in 2016, a team of astronomers led by Christopher Consellis took a much closer look at the data. They used mathematical models to account for all the galaxies we can't actually see, the ones that are too small, too faint, too far away for even our best telescopes to detect. And when they ran the numbers, the count jumped by a factor of 10, from 200 billion to 2 trillion. Most of those 2 trillion galaxies are small, tiny dwarf galaxies, faint and dim and invisible to us at these distances. But they're there. Billions and billions of them, scattered across the observable universe, each one a gravitational island containing its own stars, its own planets, its own story. And here's what makes that number truly humbling. That's just the observable universe, the part we can see, the universe beyond our horizon. The part we can never observe, almost certainly contains more galaxies, possibly enormously more. If the universe is infinite, the number of galaxies is infinite too. 2 trillion is just what we can count. And even that count, that staggering, swimming pool-filling, mind-shattering number, is almost certainly an underestimate. The Milky Way is one of 2 trillion. Not special among them, not unique, just one. One galaxy among an ocean of others, most of which we will never see, never study, never know anything about. 2 trillion worlds. And we live in one. In 1995, the Hubble Space Telescope did something that changed how humanity sees the universe forever. The mission team pointed the telescope at a tiny patch of sky. Tiny. A region so small that if you held up a grain of sand at arm's length, it would cover it. That's how small the patch was, and they let it stare. For 10 days straight, Hubble collected light from that one little patch of darkness. Light that had been traveling for billions of years, before it finally reached the telescope. And when the image was assembled, when the team looked at what Hubble had captured, the result was staggering. That tiny patch of sky, that speck of darkness that looked like absolutely nothing to the naked eye, was packed with galaxies. Thousands of them. Thousands of entire galaxies, each one containing billions of stars, all crammed into a region of sky so small you could cover it with the tip of your finger. Some of those galaxies were close, relatively speaking, bright and sharp and detailed. Others were incredibly distant, faint smudges of light from galaxies that existed when the universe was very young, light that had been traveling for over 10 billion years before it reached Hubble. We were literally looking back in time, and here's why the Hubble Deep Field mattered so much. Before that image, people had a vague sense that there were a lot of galaxies out there. But vague. The deep field made it visceral. It took a patch of sky that looked empty, that any person would have looked at and seen nothing, and revealed it to be teeming with galaxies. And if that one tiny patch was that full, what about the rest of the sky? What about every other direction you could point a telescope? The answer was obvious. Everywhere. Galaxies everywhere. In every direction. In every patch of sky. The universe wasn't sparse. It was dense, overwhelmingly, stunningly, almost absurdly populated with galaxies. The Hubble Deep Field didn't just show us galaxies, it showed us the scale of the cosmos in a way that numbers alone never could. It showed us that the darkness between the stars isn't empty, it's full. And the Milky Way, sitting in one tiny corner of all of that, is just one thread in an impossibly rich tapestry. Hubble changed everything. But Hubble had limits. It could only see so far, so deep, so far back in time. And in 2021, its successor launched, the James Webb Space Telescope. And what it has shown us so far has genuinely surprised astronomers. Not a little, a lot. Webb sees in infrared light. Light with longer wavelengths than what Hubble was designed to detect. And that matters enormously, because the most distant galaxies in the universe, the ones that formed when the universe was very young, have had their light stretched by the expansion of space. Stretched so much that by the time it reaches us, it's no longer visible light. It's infrared. Webb can see it. Hubble couldn't. And the galaxies Webb is finding at those extreme distances, galaxies that formed less than 1 billion years after the Big Bang, are not what astronomers expected. They're bigger than they should be, more massive, more fully formed. According to our best models of how galaxies form, the early universe should have been full of tiny, primitive, barely there collections of stars, building blocks, raw material, not the substantial, well-developed galaxies Webb is actually finding. Some of these early galaxies are 10 times more massive than our models predicted. 10 times. That's not a small discrepancy. That's a sign that something in our understanding of how galaxies form and grow is incomplete. Webb is also peering deeper into the cosmic web, mapping the structure of the universe at distances we've never been able to reach before, studying the atmospheres of distant exoplanets, capturing stunning images of nebulae and star-forming regions in unprecedented detail. Every few months, a new discovery comes out of Webb that forces astronomers to rethink something they thought they already understood. And here's what that means for the Milky Way. Every time Webb reveals something unexpected, it changes the context in which our galaxy exists. The universe is stranger than we thought, more populated than we thought, more active in its early life than we thought. And the Milky Way, sitting inside all of that, is part of a story that is still very much being written. Webb isn't done, not even close. The discoveries are going to keep coming. And every single one is going to make the universe feel a little bigger, a little wilder, a little more surprising than it did before. We talked about the observable universe being 93 billion light-years across, a bubble, a horizon. But here's a question we haven't fully answered yet. What do we actually see when we look at the edge of that bubble? What's at the cosmic horizon? And the answer is one of the most beautiful and strange things in all of science. At the very edge of the observable universe, the farthest back in time we can look, we don't see galaxies. We don't see stars. We see light, a faint, uniform glow that fills the entire sky in every direction. It's called the cosmic microwave background, the CMB, and it is the afterglow of the Big Bang itself. Here's what that means. In the very early universe, just after the Big Bang, everything was incredibly hot and incredibly dense. Matter and energy were packed together so tightly that light couldn't travel freely. It was trapped, bouncing around, colliding with particles, unable to move in a straight line. The universe was opaque, like fog so thick you couldn't see through it. But about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. And the moment that happened, light was released. For the first time, photons could travel freely through space, and they did, in every direction. And some of those photons are still traveling, right now. After 13.8 billion years of crossing the universe, they're reaching us, and we can detect them. They arrive from every direction, a faint whisper of radiation left over from the moment the universe became transparent. The CMB is the oldest light in the universe. It's a snapshot of the cosmos at 380,000 years old, a baby photograph of everything that exists. And it contains information. Tiny variations in the temperature of that light, differences of fractions of a degree, tell us about the density fluctuations that existed in the early universe. The same fluctuations that eventually grew into galaxies, superclusters, and the cosmic web. We are literally looking at the seeds of everything. The CMB is the edge of the observable universe, the farthest we can see, and it is the birth cry of the cosmos itself. Here is a question that has haunted philosophers and scientists for centuries, and the honest, uncomfortable answer is that we don't know. Is the universe infinite? Does it go on forever? Or does it have an edge, a boundary, a size? We genuinely, truly, fundamentally do not know. And here's why. The observable universe, the part we can see, is finite. It has a size. 93 billion light-years across. We've established that. But the observable universe is not the universe. It's just the part we can see. Beyond our cosmic horizon, the universe almost certainly continues. The question is, how far? And there are only two possibilities. Either the universe is finite, meaning it has some size, some total extent, some boundary or curve that brings it back on itself. Like the surface of a sphere, you could travel in one direction forever and eventually end up back where you started, even though you never hit a wall. Or the universe is infinite. It goes on forever, in every direction. No edge, no boundary, no end. Just more space, more matter, more everything, stretching out eternally. And here's the thing. Both of these possibilities are terrifying. If the universe is finite, it means there is a fixed amount of everything. A finite number of stars, a finite number of galaxies, a finite number of possible places life could exist. If the universe is infinite, then everything that can happen is happening somewhere. Every possible arrangement of matter exists somewhere in the infinite expanse, which means that somewhere out there, in some distant, unreachable corner of an infinite universe, there is another you, reading this exact sentence in an identical galaxy. Right now. Some physicists take that seriously. Others think it's an absurd implication of taking infinity too literally. The truth is, we have no way to test it. No telescope can see beyond the observable horizon. No experiment can probe whether space curves back on itself or stretches forever. It might be the one question science can never definitively answer. The universe might be infinite, and if it is, the Milky Way isn't just small. It isn't even a measurable fraction of the whole. 0% of infinity is still zero. Here's something that sounds simple, but completely rewires how you think about space. The universe is expanding. Right now, as you listen to this, the universe is getting bigger. And it's not doing it because galaxies are flying apart like shrapnel from an explosion. That's the mistake most people make. They picture the Big Bang as some kind of detonation, with everything blasting outward from a single point. But that's not what's happening. It's not the galaxies that are moving, it's the space between them that is stretching. Think of it like dots drawn on a balloon. If you inflate the balloon, every dot moves away from every other dot. But none of the dots are moving across the surface of the balloon. The balloon itself is getting bigger, and the dots are carried along with it. That's what's happening to the universe. Space itself is expanding. Every point in space is moving away from every other point, and that means there is no center, no special location from which everything is expanding outward. It looks the same from everywhere. If you were on a galaxy a billion light-years away, looking out at the cosmos, you would see the exact same thing we see. Everything moving away from you, in every direction. You would conclude that you were at the center of the expansion, but you wouldn't be. Because there is no center. The expansion is happening everywhere, uniformly, in all directions, at all points in space simultaneously. And here's what that means for the Milky Way. Our galaxy is not special in this picture. It's not in a privileged location. It's not at the center of anything. It's just one galaxy among trillions, carried along by the expansion of space like every other structure in the universe. The distances between galaxies are growing, not because anything is moving through space, but because space itself is growing, and that expansion is accelerating. Something, which we call dark energy, is pushing space apart faster and faster. The universe isn't just expanding, it's expanding faster every year. And billions of years from now, that acceleration will push most galaxies beyond our observable horizon forever. The universe will look emptier and emptier, not because matter disappears, but because space stretches it beyond our reach. Let's talk about the future. The long future, the deep future. Because the Milky Way has a story still to tell, and parts of it are already written. We know what's coming. We just have to wait a very, very long time to see it. First, the collision. In about 4.5 billion years, the Milky Way and Andromeda will meet. We talked about this earlier, but let's zoom out and look at the full timeline. The two galaxies will approach each other over billions of years. They'll pass through one another. Then gravity will pull them back. They'll pass through again and again. Each pass, the two galaxies will lose energy, shed stars, and gradually lose their spiral structure. Over the course of several billion years, the chaos will settle, and what emerges, roughly 6 billion years from now, will be a single, massive elliptical galaxy, Milkomeda, containing about 1.5 trillion stars, a giant. By that point, the Sun will already be nearing the end of its life. In about 5 billion years, the Sun will swell into a red giant, engulf Mercury, Venus, and possibly Earth, and then shed its outer layers, leaving behind a white dwarf, a cold, dense remnant. So by the time Milkomeda fully forms, the Sun as we know it will be gone. But the galaxy will remain, and it will continue. Milkomeda will drift through the universe, slowly consuming smaller satellite galaxies, growing marginally larger over time. But the universe is expanding, and that expansion is accelerating. Over tens of billions of years, the galaxies beyond the local group will be pushed further and further away, beyond our horizon, vanishing into the darkness. Eventually, Milkomeda, and whatever remains of the local group, will be the only structure left in our observable universe. Everything else will have been carried away by the expansion of space. And then, over trillions of years, even the stars in Milkomeda will burn out. One by one, the suns will die. The galaxy will go dark, cold, silent. The matter will slowly decay. Black holes will evaporate. And eventually, after an incomprehensible span of time, there will be nothing left but empty, expanding space. That's the fate of the Milky Way. Not destruction, not explosion, just a slow, quiet, inevitable fade into the dark. Let's do this one more time. From the beginning, but this time all at once. One continuous journey, no stops, no pauses, just the scale building and building and building until it becomes something you can actually feel. You are here, on Earth, a small rocky planet orbiting an ordinary star. That star, the Sun, sits in the solar system, a collection of planets and moons and debris, stretching out about a light year in every direction if you count the Oort cloud. That solar system sits inside a stellar neighborhood, a few hundred stars scattered across 100 light-years of space, mostly empty, quiet. That neighborhood sits inside the Milky Way, a disk of 100,000 light-years across, containing between 100 billion and 400 billion stars, spinning slowly around a supermassive black hole at its center. The Milky Way sits inside the local group, a collection of 50-plus galaxies stretching across 10 million light-years, dominated by two giants, us and Andromeda. The local group sits inside the Virgo supercluster, a structure containing over 100 galaxy clusters spanning 110 million light-years, with the Virgo cluster at its gravitational heart. The Virgo supercluster sits inside Laniakea, a supercluster of superclusters, 100,000 galaxies, 520 million light-years across, the largest structure we can confidently say we belong to. Laniakea sits inside the cosmic web, a vast network of filaments and voids stretching across the observable universe, with structures like the Hercules Corona Borealis Great Wall spanning 10 billion light-years. And all of that, every single piece of it, sits inside the observable universe. A bubble 93 billion light-years across, containing 2 trillion galaxies, which itself might be just a tiny fraction of a universe that could be infinite. That's the full picture. That's the chain. Earth to Sun, to solar system, to stellar neighborhood, to galaxy, to local group, to supercluster, to cosmic web, to observable universe, to the unknown. Every step is bigger than the last, by factors that break the brain. And at every single step, the Milky Way gets smaller. Not physically. It's still 100,000 light-years across, but in significance, in proportion, in the grand, staggering, beautiful context of everything that exists. You started this video looking up at a band of light in the sky. Now you know what it is, and you know where it sits, and that knowledge is everything. Here's the last thing I want to leave you with, and I want you to really hear it, not just process it. Hear it. Every atom in your body was made inside a star. Every single one. The carbon in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was forged in the nuclear furnaces of stars that lived and died billions of years before the sun even existed. Stars that burned bright, ran out of fuel, and exploded, scattering their guts across space. And that scattered matter, that stellar dust, drifted through the void for millions of years until gravity pulled it together again. Into clouds, into new stars, into planets, into you. You are not separate from the Milky Way. You are not living inside it the way you live inside a house. You are made of it. The Milky Way didn't just give us a home. It gave us our bodies, our atoms, our chemistry. Everything we are is a direct product of stellar processes that happened inside this galaxy over billions of years. The stars that made you are dead now. Most of them burned out long before the sun was born. But their legacy is here, in you, in me, in every living thing on this planet. We are, quite literally, the galaxy looking at itself. The Milky Way spent 13 billion years making stars. Those stars made heavier elements, those elements made planets. One of those planets cooled, and water collected on it, and chemistry became biology, and biology became consciousness. And now that consciousness is sitting here, looking back up at the galaxy that made it, and understanding for the first time what it's seeing. That is extraordinary, not because the Milky Way is big, not because it contains hundreds of billions of stars, but because out of all that vastness, out of all that emptiness, out of all those trillions of galaxies and quadrillions of stars scattered across an observable universe that might be just a fraction of an infinite whole, somewhere in one quiet corner of one ordinary spiral arm, matter arranged itself into something that could ask why. The Milky Way is vast, the universe is vaster, but you are here, awake, aware, made of stars, looking up at the sky, and finally truly understanding what you're looking at. That's not small. That's the most remarkable thing in the universe.